Welcome to Chapter 8. This is on linear momentum and collisions. Linear momentum is another really fun thing to use because momentum is conserved. So just like energy is conserved, and we could talk about velocities as objects drop off a roof, momentum is conserved, and so we can look at velocities during collisions of one sort or another. So linear momentum is the mass multiplied by the linear velocity. So anything that's moving has some sort of linear momentum. The symbol for linear momentum is lowercase p. So little p is equal to little m times little v. Momentum equals mass times velocity. It is a vector. It is a vector. So not only does it have magnitude, but it has direction. Momentum is measured in kilogram meters per second. The mass is in kilograms and the velocity is in meters per second. The direction of your momentum is going to be determined by the direction of the velocity. And if we went back, we always like in physics to say, if you went back and looked at Newton's second law, you remember Newton's second law? F equals ma. If you looked at it, it was actually originally stated in terms of momentum. And you can follow the little logical progression to go from force is equal to change in momentum over change in time to force is equal to mass times acceleration. There's some homework problems in Chapter 8, and there will be some problems on your study guide as well. So let's look at conservation of momentum and collision and impulses. So for momentum is conserved, the total momentum of your isolated system of bodies is equal, before an event is equal to the total momentum after the event. So if you think about you're firing a gun, before you fire the gun, there's a bullet in the pistol. We'll make this a pistol. There's a bullet in the pistol. Everything is sitting still, so the momentum before you pull the trigger is zero. At the instant you pull the trigger, the bullet moves right, but the gun recoils left. And the total momentum of this system after you've pulled the trigger has to add up to zero because our starting momentum was zero. So momentum before has to equal momentum after. And we'll do a gun example. So let's do one. So the recoil velocity for a 1 kilogram gun, if a 10-gram bullet is shot with a speed of 500 meters per second. So the mass of the gun, remember gun would be a little subscript, so it would be below the line. I can't make it do that for some reason. And bullet is a subscript, so below the line. So the mass of the gun is 1 kilogram. The mass of the bullet is 10 grams. Ah, they're trying to trick us. 10 grams has to be converted to kilograms because we are using MKS units. So 10 grams, move the decimal 3 places to the left, or Google it. 10 grams is 0.01 kilograms. The velocity of the bullet after you pull the trigger is 500 meters per second. And the velocity of the bullet before you pull the trigger is the same as the velocity of the gun before you pull the trigger is zero. And what we want to know is, what about the gun? If the bullet's going 500 meters per second, how fast is the gun moving? So momentum is mass times velocity. So little p is equal to little m times little v. And momentum before equals momentum after. P before equals p after. So we will set it up. P before equals P after. Momentum is mass times velocity. So mass times velocity of the gun plus mass times velocity of the bullet, both of them before, notice I've got brackets here, equals mass times velocity of the gun plus mass times velocity of the bullet, both of them after. Brackets are our friend. Subscripts are our friend. The mass of the gun before is 1 kilogram, but the velocity is zero. Mass of the bullet is 0.01 kilograms, but its velocity is zero. On the right-hand side, the mass of the gun is 1 kilogram. The velocity of the gun after is what we do not know. mass of the bullet after is 0.01 kilograms, and its velocity is 500 meters per second. On the left-hand side, the momentums are zero. If you have zero velocity, you have zero momentum. So we've got 1 kilogram times the velocity of the gun after, plus, well, 0.01 times 500 is 5, and the units would be kilogram meters per second. To get rid of the 5 on the right-hand side, we have to subtract 5 from both sides, so negative 5 kilogram meters per second. Don't lose that minus sign. Negative 5 kilogram meters per second equals 1 kilogram times velocity of the gun after. Divide both sides by 1 kilogram to get it equal to velocity of the gun after. And we see that negative 5 divided by 1 is negative 5. Kilograms cancel, and it leaves us with meters per second. So what the minus sign tells us that the gun is going in the opposite direction from the bullet, and much slower. When you fire a pistol or a rifle, there's always some sort of recoil associated with it. So that's why with rifles, they have, if you've got a hunting jacket, the shoulder has padding on it because you're supposed to nestle the butt of the gun against your shoulder, not inches in front, but against it, so that the gun doesn't slam into you and hit you, but there is recoil, and you can be sore if you're unaccustomed to it. This is also why when you go and you look at pirate ships someplace, or historic ships, the guns on deck are mounted so that they roll back. They're attached, but they roll. So you may have seen some sort of museum or old movie where they were shooting large guns or cannons. They have a mechanism in place so that the gun itself can roll back. If it didn't, what would happen over time is the gun would loosen the bolts holding it to whatever it's fastened to, and these big like anti-aircraft guns or cannons on ships or things like that, what they would do if they were not free to roll a little bit for the recoil, they would eventually dislodge from where they're mounted, and that would be bad. Okay, recoil. Let's talk about two cars that hit. It could be two cars, it could be two rugby players. Rugby always looks like a free-for-all to me. Two rugby players or two football players in a tackle. Now, I'm going to take a special case and we're going to have them lock bumpers. If you don't have them lock bumpers, if they slam into each other and they bounce off and go different directions, it's just a much harder problem to solve. So I think we'll stick with locked bumpers. So mass 1 is 1,000 kilograms, mass 2 is 800. The velocity of car 1 before is 10 meters per second east, so that must be my red car, it's going right. For car 2 before, that must be the brown car, it's going left, 15 meters per second west. And we want to know, what are they doing after they snag bumpers? Which way will they go and how fast? So we will set it up. We know mass 1 is 1,000 kilograms, velocity 1 before is 10 meters per second east. Mass 2 is 800 kilograms. Velocity 2 is 15 meters per second west. And if we make east positive, that means west is going to be negative 15 meters per second. We're trying to find velocity after. And we know that momentum is mass times velocity, and momentum before equals momentum after. So we set it up. Momentum before equals momentum after. So mv for 1 plus mv for 2 before equals mv for 1 plus mv for 2 after. So car 1 has a mass of 1,000 kilograms and he's going 10 meters per second east. Plus car 2 is 800 kilograms going negative 15 meters per second. That minus sign is there because he's going west. Equals the mass of car 1, which is 1,000 kilograms, times, I've just got V after. Why do I just have v after? Because they lock bumpers. They don't have a separate velocity. Car 1 and car 2 have the same velocity, v after. So 1,000 kilograms times v after plus 800 kilograms times v after. Okay, 1,000 times 10 is 10,000 kilogram meters per second. 800 times negative 15 is negative 12,000 kilogram meters per second equals 1,000 kilograms times v after plus 800 kilograms times v after is the same thing as saying 1,000x plus 800x. The numeric coefficients add because of this plus sign right here. So 1,000 plus 800 is 1,800 kilograms. 1,000 plus 800 is 1,800 kilograms. And it's all times, this sum is times v after. So 10,000 minus 12,000 is negative 2,000. Don't miss the minus sign. Divide both sides by the 1,800. And we have that v after is negative 1.11 meters per second. The negative means it moves west. And you've got to include, if you've set up like east is positive and you end up with a minus, you can't just tell me it's got a negative velocity. You have to tell me it's going west. So some homework problems, and there's some study guide questions as well. So collision and impulse. Impulse is change in momentum. And what is important is this part of the relationship. The force times the change in time equals the change in the mass times the velocity. So what we'd like to do is see about how do changes impact your end result. So suppose you are using a hammer and you're very slowly tapping on a nail. So the hammer might have a pretty big mass, but it's got a little velocity. So doesn't have a very big impulse. And what's going to happen is it's not going to have a very big force. If you want to drive a nail in, you have to put some muscle into it. This little bitty tap, 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 tap will not get your nails driven. It'll save your thumb, but it won't get the nails driven in. So let's look at other things. The net under a high wire act. The net is very flexible. Maybe you've been to the circus or you've seen it on television. It is very flexible. And it's flexible because we want to have a really large delta T. We want to take a long time to slow down, because if your delta T is large, your force is going to be small. You could put a steel plate under that high wire and say, okay, drop off the high wire, land on the steel plate. But you would stop really quickly. And that little itty bitty delta T would give you a really large force on impact, and it would hurt. So long stopping time reduces the force, which anybody knows if they've slammed on their brakes versus gradually stopping. Collapsible barriers on highways. So sometimes you'll be driving along and you'll see a bunch of those big orange barrels around maybe a abutment to an overpass. And they're there so that if you run into them, they take the brunt of the force and you slow down gradually rather than hitting the concrete wall and stopping. Or take the guardrails that you'll see on roads. The guardrails are not so much there to keep you from going over, but to slow your, to elongate your stopping time, to make it take longer for you to come to a stop and keep you from going over the edge. But you want to really increase your delta T. So let's look at conservation of energy and momentum in collision. So in an elastic collision, it's perfectly elastic, kinetic energy and momentum are conserved. Kinetic energy and momentum are conserved, and you don't have lost energy, so no dissipated forces. And you just look at conservation of kinetic energy and conservation of momentum and use them appropriately to solve your problems. In the real world, most collisions are inelastic. Kinetic energy is almost never completely conserved. There's almost always a sound, there's almost always some friction going on, but momentum is conserved. So in our elastic collisions, momentum is conserved. And those inelastic. So momentum's conserved in both. Kinetic energy is only conserved in elastic ones. All right, just a brief mention about rocket propulsion. We're not going to do anything with it. I just wanted you to remember that it is an action-reaction. So think of it like if you filled up a balloon and then you let it go, you didn't tie it off, but you let it go, the air gushes out the end. And so as the air forces out, the balloon goes the other way. People will sometimes do this like in middle school. You'll tape your balloon to a soda straw and thread the straw through a string and watch it move across the room that way. So it's a very simplified version of rockets go up. It's all because of Newton's third law. For every action, there is an equal and opposite reaction. The air escaping from a balloon. So an octopus actually forces water through it. So water comes in, it circulates around, it goes out, and the octopus goes forward. So we can use conservation of momentum to a certain extent if you're talking about rocket acceleration, but like I said, it's way more complicated than just a simple explanation. But anyhow, it's a start. So we'll stop with this.